So I'm going to do some examples for partial derivatives. So first example, we have f of xy equal to x squared e to the negative xy over 2. And we want to find f of fx and fy. So df dx is going to be partial derivative with respect to x of this function. And we have two functions of x multiplying each other, so we're going to have to use the product rule. So first we'll take the derivative of this, we'll multiply by this function, and then we'll add that to the derivative of, or the first function times the derivative of the second function. So derivative of x squared with respect to x is 2x. So 2x times e to the negative xy over 2 plus x squared times derivative of this. So we just rewrite the function e to the xy over 2. Then we take the derivative of what's on the inside with respect to x, the partial derivative with respect to x. And the partial derivative of that with respect to x is just negative y over 2, because y is a constant, 2 is a constant, we pull it out, and the negative sign, and then derivative of x is just 1. So we rewrite this as 2x e to the negative xy over 2 plus, or minus, x squared y over 2 times e to the negative xy over 2. And I think it's sufficient to leave it like that. If you want, you can factor out this, an x and an e to the xy. And we can also pull out a 2. So we're left with a 4 here, and a, because we factor out 1/2 from this, we have a 4, we factor out the x and the e to the negative x y over 2, and we're left with a y here, or xy. Right, so that is our answer. And for df dy, we're taking the y derivative of this. So, and this would be easier because we only have one function of y. X squared is just a constant in this case, so we pull that out. We're taking the partial derivative with respect to y, with respect to y, of e to the negative xy over 2. And that's just going to be e to the negative xy over 2 times the partial derivative of negative xy over 2 with respect to y. And that's just x squared times e to the negative xy over 2 times negative x over 2. You can rewrite that as negative x to the third of over 2 of e to the negative xy over 2. Okay, and now moving on to our next example, we have h of u and v, so we don't always need x and y, we can use different letters. Equals e to the u sine u plus v, and we're told to find hu of 1, negative 1. So we're just finding one partial derivative here, and we're evaluating it at a point 1, negative 1. So hu is going to be d h du, so d du of e to the u sine u plus v. So again, we're going to use product rule. We're going to take the derivative of this with respect to u, multiply it by this function sine u plus v, add that to this function times the derivative of sine u plus v with respect to u. So derivative of e to the u is just e to the u times sine u plus v, and we have e to the u again. Derivative of sine u plus v, we're going to have cosine u plus v times, using chain rule, du, but that's just going to be 1. So just forget about that. You can factor out e to the u here, so we have e to the u times sine u v plus cosine uv. And that is our hu of uv. But now we want hu of 1, negative 1. So wherever we see a u, we're going to plug in 1, so we have e to the 1 times sine, and we have u as 1, v as negative 1. And we have cosine u plus v, so cosine 1 plus negative 1. So we have e times sine 0 plus cosine 0. Sine 0 is just 0, cosine 0 is just 1, so our answer is E. Our next example, we have 3 variables. We have f of x, y, z equals e to the yz sine x. So we want to find fx, fy, and fz. So fx is just this derivative with respect to x of this. This is just a constant in this case, so you can pull that out. Derivative of sine is cosine, and that's our fx. For fy, we're taking the derivative with respect to y of this. So we can pull sine x out as a constant. And taking the derivative of this with respect to y, that's just the exponential again, times the derivative of the exponent with respect to y. Well, you can pull a z out as a constant, and derivative of y with respect to y is just 1. So we have z times e to the yz sine x. That's our fy. And fz is the derivative with respect to z of e to the yz sine x. And by the same process, we can pull sine out, and we have derivative with respect to z of that exponential, which is just the exponential times the derivative of the inside. Pull the y out, derivative with respect to z of z is 1, so we have y e to the yz sine x. That's our f of z. And we'll have one example with a mixed derivative, so
I'm ready. What you got for me?
g of st equals ln s squared plus 3st, and we want to find d squared g dt squared, d squared g dt ds, and d squared g ds squared. So we'll first differentiate this with respect to t, and for ln we have 1 over the inside of the function, and we're going to multiply by the t derivative of what's inside the function. So this will go to 0, and this will just be 3s, so we'll have 1 over s squared plus 3st. Actually, we'll have 3s over s squared plus 3st. And we can factor out an s and cancel it. So we have 3 over s plus 3t. That's our dg dt. So now to find the second derivative with respect to t, we take the t derivative of this, s plus 3t, and we pull out a 3, and we take the derivative of what's left. So we just use a chain rule. This is going to be 3 times. This is a s plus 3t to the negative 1 power, so we can pull that negative 1 out to the front, make it a minus 3, times s plus 3t to the negative 2, and then we're going to take the t derivative of s plus 3t, which is just going to be 3. We'll have negative 9 over s plus 3t squared. So that's our d squared g dt squared. Now, if we take this result, which is dg dt, and we differentiate that with respect to s, by the same logic, I'm pulling 3 out, and I won't give this one as much explanation. So this is d squared g ds dt, but since we're looking for dt ds on the bottom, we can remember that these mixed derivatives are equal no matter what the order of taking partial derivatives is. So that's the box of answers here. So now we want to find the second derivative with respect to s, so we're going to have to start over. So we're going to take the s derivative of ln s squared plus 3st. So we're going to have 1 over s squared plus 3st times the s derivative of s squared plus 3st. That's going to be 2s plus 3t over s squared plus 3st. And if we actually pull out an s from the bottom, oh no, it won't work. Never mind, sorry. So this is our s derivative. So now if we want to do the second derivative with respect to s, we're going to have to use the quotient rule. So we have the bottom, s squared plus 3st, derivative of the top with respect to s, so 2s plus 3t, minus the top, 2s plus 3t, derivative of the bottom, which is s squared plus 3st, all over the bottom squared, s squared plus 3st squared. So, doing this calculation, and that's pretty much as far as I'm going to simplify it. This is our d squared to ds squared.